All right, hello everyone. Welcome to lesson 2.5. This will actually be fairly short. Just setting up for some stuff we're going to talk about in a little more detail next week. Linear regression models, okay? We're going to introduce this idea today, but really dig into the details later because there can be a lot of nuance to this topic, even if on first pass here it'll seem fairly simple. But I do encourage you to pay attention to the little details that I mentioned because they're important too. Just because it doesn't seem like a big deal doesn't mean that it's not. All right, a few announcements. Please, you need calculators. We're using them like all the time now. So some people came by this week. There's still like a few who told me they need them that I've not heard from at all. It's going to be real difficult moving forward if you don't have a calculator. Please reach out to me. Also, tentative Unit 2 exam next Friday, but I really do think I'm just going to end up pushing it back to the following Monday. And don't forget that office hours will be posted today. That's Friday. Office hours are at 12. That is an incorrect time. 12:50 on Monday, okay? And you'll see those names posted this week. Some people I want to talk to just to make sure you're feeling okay about our Unit 2 work. In Unit 2, we are exploring two variable data, looking at relationships between two variables, and talking about whether or not apparent patterns and associations are random or not. All right. So today we're talking about what's called regression lines, or a regression line. A regression line, you can think of it as simply a summary of the pattern on a scatter plot. You've probably just started to see these r-squared things float around. We're going to talk about that next week, what this r-squared means. But for now, take a look. Here's a kind of comedic take on scatter plots. We have a linear regression line right here going through the scatter plot. It is a pretty widespread scatter plot. So the joke that they're making here is that, well, it's hard to tell if we have such a non-correlated scatter plot here, whether this linear regression line is even any good. So let's dig a little more into this idea. A regression line here models the linear relationship between two quantitative variables when one variable helps explain the other. Three important things there. One, we're talking about a linear relationship. Two, we're measuring two quantitative variables. Neither of them can be qualitative, categorical. And one variable has to help explain the other. So this is different than correlation. Correlation does not actually require an explanatory variable per se, just a relationship between the two variables, because correlation is just a measure of strength and direction, not necessarily whether or not one explains the other. All right, so we're really looking at those three big ideas: linear, two quantitative variables, and one variable helps explain the other. And so the joke over here is that, well, with a scatter plot that has such a low correlation, if you calculated this scatter plot's correlation, it would be really close to zero, frankly. It's hard to trust linear regression, a line that models, quote unquote, this plot, because it's so widespread. In fact, the joke is it looks more like a constellation of things. So how can we do linear regression? And we'll get more into, again, how this r-squared connects to that next week. So what is a regression line? Well, it actually follows what you're probably familiar with. It models how a response variable, we'll call y, changes as an explanatory variable called x changes. And we write it out in this form. We call this thing right here y hat. Y hat is the predicted value of y for some relationship given some x value. I know in algebra we're used to saying mx plus b. Please, in stats, shift that thinking. We're going to do a, the y-intercept first, plus bx, the slope, and then x, which is our explanatory variable. Y hat is going to be the predicted value of the response variable. Y hat, the predicted value of the response variable. So let's actually do this. Let's look at the price of trucks sold on autotrader.com. So this is 8 trucks pulled from autotrader.com. I believe these are all F-150 Super Crew 4x4s, if I want to be real specific. And let's assume that the miles driven, explains the price of the truck, which is probably a fair assumption. Generally, the more miles on a vehicle, the lower the resale price is. So the data from 8 trucks are given here. Let's create a scatter plot and find a linear regression equation, a linear regression model to explain the cost of trucks as explained by the miles driven. All right. I'm going to pull up my calculator here. I'm going to walk through some calculator things. All right. For those who have not watched my video yet, for the calculator, you do need to make sure that diagnostic is on for basically the rest of this course. So if you click second catalog, it'll take you to the catalog. You scroll way down to DIA. Oh, there we go. Past it. Go too far. All right. Diagnostic on. We'll hit enter. Boom. There we go. All right. So let's enter these data, or data is plural, these data into our table. So if you click stat, edit, we'll be able to enter our data into the table here. If you need to, we can clear any data that's actually there in L1. And L2, you just scroll up to the top where the list is named and clear it. Hit enter. All right. So in list 1, we're going to do 70,583 and hit enter. I'm just going to list out all the miles driven. Please go ahead and do that on your calculator. 129, 484, 29932. And double check, because sometimes things don't respond the way you would hope for them to. 29932. There we go. 29953. 24, 495, 75, 678. That's kind of fun. 8359 and 4447. All right, now we go into list 2. We're going to put the prices of each of these vehicles. 21,994, 9500, 29,875, 41,995, 41,995. Interesting. 28,986. 31,891. And 37,991. All right. Again, I like to do a quick scan just to make sure I haven't made any mistakes, because getting one of these points of data off will change our answer here. I'm going to do a quick skim faster than I would typically. If I've misentered something and I just continue, just bear with me. Just assume I did it all correctly, because the calculator steps will be the same. All right, cool. So we enter it into list 1 and 2. Remember, we can make a scatter plot from this if we would like. If we want to make a scatter plot from this, we can do second y equals, and we have stat plots. It's going to plot right now. I've already turned on plot 1, but if you need to, you can hit enter, turn it on. Make sure you're taking from list 1 and list 2. If you ever need to change those lists, you can scroll down to them. Notice above 1 is L1. You can hit second 1, and it'll type L1 in there so it knows what list to go from. We're going to do a scatter plot. They're going to be in blue. All right, so I can graph that. We're probably not going to see it because look at our numbers. We need to change our X and Y scale so it fits these numbers. So I'm going to go ahead and do that. I'm going to make my window, let's see, my L1 was in my X direction. That's my explanatory variable. My smallest one is 4,447. So let me just go ahead and go from like, let's go ahead and do, well, it spans a lot. So actually, let's just do 0 until, what's our biggest one? 129. Let me go up to 145,000 in the X direction. And I'm going to go by, let's go a scale of 10,000 there. And my response variable, my Y values here, smallest one is 9,500. For now, just to get a glimpse of it, let me go from 0 until, what's my biggest one? 41 something. Let me go from 0 to 50,000, also going by 10,000. And let's just see if that helps. Okay, that's not bad. Okay, we'll keep that. Cool. Here we go. All right, it looks like we got a pretty, if we describe this, negative, right? Negative is our direction. A negative, maybe moderately strong, linear relationship here. Doesn't look like we have Any outliers or anything? Maybe this one, depending. We don't have a ton of data points. Maybe this one over here, we could say is an outlier, but we got this weird sort of grouping where we have one here, two here, and one here. So maybe we can tell this is an outlier. I've actually shortened this data set so that it is only 8 points instead of 16. In the full data set, I will promise you that this is actually not an outlier. So there we go. But for now, there we go. Negative, linear, moderately strong association looks like there. Okay, so we have the scatter plot. So how do we get our linear regression? Well, the linear regression is relatively easy to get. We go to Stat, scroll over to Calc, scroll down to lin, L-I-N, reg. See it says A plus BX. Hit enter. We want to pull L1 is our explanatory variable. L2 is our response variable. What's nice about this, though, is we can actually store, if we want to, the equation it gives us. We can store it somewhere. Let's go ahead and store this equation, if I can remember how to do this correctly, in our y1. So to do that, click vars. Actually, let's go back. We'll go back over here. I started doing it without. Okay, so if we want to store it somewhere, you go down to that line. Now let's hit vars. That stands for variable. Scroll over to y vars. Go to function, y1, and we're going to store our equation in y1. And let's hit calculate. All right. Oh my gosh, look at this. It gives us, here's the form of the equation. Here's what A is. Here's what B is. There's our R squared. We're going to talk about that next week. There's our R value. It looks like they have reasonably strong correlation here. All right. And if I've done this correctly, you could write these numbers down on your paper and store and have them hard for later. But I think if I've done this correctly, it should be in y1 also. All right, cool. So notice up here, we have it stored in here in y1. There is our linear regression, our simple linear regression equation here. Boom, boom, boom. If I graph it now, oh my gosh, there is the line as well. That's really nice, super convenient. So we now have our scatter plot with our linear regression model going through it. All right. I want to keep this calculator because we got some questions now that I want to talk about with these. All right. Cool. So we now are told use the model to predict the price of a truck that has driven 100,000 miles. Well, we know what the model is. If you wrote this out by hand, what the actual linear regression model is, if we want to use the model to predict the price of a truck that has driven 100,000 miles, remember our general form of our linear regression is this, right? So if I plug in x, and remember my explanatory variable is miles driven, if I plug 100,000 miles into x and work that out, it should tell me the predicted price of the truck. Because remember the y value, the response variable, is the price. So if I simply plug in x is 100,000 into this, it will tell me the predicted price of the truck. So how do we do that on the calculator? It's actually pretty quick on the calculator. If you click second, calc, and you do value, it'll say x equals, and we can simply type in 100,000. If you want to, you can do this by hand too. Write down your equation, plug in, quote unquote, 100,000, and kind of move on with our lives. So I'm going to go ahead and hit enter, and it'll tell us the predicted value here is 18671. Start typing, didn't do anything. 18671 point, we'll round to 62 cents since we're dealing with dollars here. 62 cents would be the predicted price of one of these trucks. Now I'm going to draw this out. I have in my mouse. Sometimes you actually see people write out these sort of equations like this, though, which seems a little goofy, but it's actually a nice way to remember this. They'll put a big hat over. What does Y stand for? Y stands for price. So they'll do like price hat. Price hat equals, and then they'll put whatever the A value was here. I'll just write A plus, or in this case it was minus a number, but plus B. And then for X, they'll actually put what the thing is measuring, miles driven. All right. So sometimes you actually see people write out like little statements like this, and that's fine if you would like to. It's not necessary, but we do want to make sure we're keeping the fact that we're looking at price hat, the predicted price. Right. Again, you can do this by hand using those numbers that we got. You can make your own equation, plug it in, and work out by hand, whatever, 40,882 point whatever, plus negative 0.22, whatever, times 100,000, work that out. But we can also just use the calculator to do it, and there we go. Our predicted price is about $18,671. So is this likely to be the actual value of such a truck? Answer here is no. This is the predicted value. Think of it as your best guess, but actually in many ways represents, it is the average value, the mean value, if you will, of a truck that has that given mileage. So this isn't, we're saying not that this is what a truck will cost. We're saying this is what we predict. It's the best guess. It's the average value of what a truck with that mileage would cost. Use the model to predict the price of a truck that has driven 300,000 miles. Okay, let's do that. Again, I could plug in to price hat. I know what A and B is. I can work that out by hand, or I can use my calculator. Second, calc, value, 300. It says, attempted to use a variable or function where it is not valid. Hold on 1 second. Maybe I made a mistake. I want to go to, did I do something? Yes, all right. So notice here, 300,000. My window only went up so far, right? So let me open up my window a little more. Let me do my window, my X maximum up to, let's make my X maximum up to like 400,000. Now we should be able to type 300,000. All right. There we go. Okay. I might have to extend my Y values, don't I? Let me make my minimum Y value down to like, I don't know. I'll be bold about this one. Maybe 100,000. That way we can see everything here. Second, calc, 300, 1, 2, 3. All right. It says the predicted value is negative $25,749. Negative 25,749 dollars and 35 cents. Now we go, well, wait a minute. Does that even make any sense? And the answer is no, it doesn't, right? Basically, that would mean if I was trying to sell this truck, I would pay you $26,000 about to take this truck off my hands. And that indicates one of the limitations of these linear regression models. What we just tried to do there was what's called extrapolation. We were trying to extrapolate from this model. Extrapolation is the use of a regression line for a prediction outside the interval of x values used to create the line. Now, when we created the line, remember, we used x values up to like 140-ish thousand. We're trying to extrapolate to something way out over here, way past that data. So an extrapolation is the use of a regression line, our equation, to predict something outside of the interval of x values used to create the line. The further we extrapolate, the less reliable the predictions get. Our prediction said we're going to end up with like, negative 25,749 as our expected price of our truck. That doesn't make any sense because we're outside of our x values we used to create the graph. For truck or vehicle prices, right, we'd actually expect this to kind of level off eventually, somewhere closer to zero, right? We expect this to level off somewhere, not keep going linearly into negative values. So this is a big caveat. Do not make predictions for x values much larger or smaller than the actual data. We are using that data, so we want to predict things kind of within or close to that data. We don't want to vary too far outside of it, because actually it is rare to have some model or some relationship actually be linear for all values of the explanatory variable. Usually things change at some point, right? Even talking about people's heights, right? If you modeled like people's heights who are aged like 4 to 16 and you continue that model, you might realize, wow, people by the time they're 32 are like 12 feet tall. But that is not the case, right? People's heights level off. Things don't continue linearly. Things do not continue linearly very long. In fact, even within the age range I gave, people have growth spurts and things. So we stick to our predictions as within the x values that we were given, or at least really close by. The farther we extrapolate away from the given x values, the worse our prediction gets. Here's a great little comment from XKCD that sort of talks about the dangers of extrapolation. This guy just got married to this woman. He says, yesterday she had 0 husbands. Today she has 1. As you can see, by late next month, you'll have over 4 dozen husbands. Better get a bulk rate on wedding cake. So extrapolating well outside of those given points is dangerous. We can't make conclusions very well from that. A couple other comments to wrap up here. Extrapolation, when we're looking at this y hat equals a plus bx. A is the y-intercept, right? And tells us the predicted value when x is 0. Sometimes that value makes sense. Sometimes it doesn't make any sense at all. You might end up accidentally saying something in a model like, oh my gosh, well, if I drove my truck 0 miles, then the predicted value would be, I don't know, like $40,000, and maybe that's well above or well below the actual price, initial price of the truck. So sometimes actually that quote-unquote y-intercept or initial value doesn't make sense in the context of the problem. It maybe misses the mark, right? Maybe if you did a scatter plot of people's heights, that it would accidentally say that when someone is 0 years old, they are like 3 inches tall, right? So you got to be careful about the y-intercept. Sometimes they're useful, sometimes they're not. B is the slope, the amount by which the predicted value of y changes when x increases by 1 unit. In our example, if I recall what I just did there, our slope was negative 0.2222. What that means is every time my truck is driven 1 mile, the value of the truck decreases by about 22 cents, because this is in dollars. Right? Because slopes, interpreting them in context is really useful. This tells us that the value of our truck changes by 22 cents for every mile driven. Because remember, slope is y value, change in the y value over change in the x value. So the change in the y value, that's miles driven. Change in the change in the y value is price, dollars, divided by the change in the miles. So it's 22 cents is lost every mile. So that slope is actually really useful and helps us kind of understand the context of the problem. But it does not tell you the strength of the relationship. Negative 0.222 doesn't mean a weak relationship. It's not an R value. It just tells us how is the Y value going to change as the X value changes by 1 unit. So it does not tell us the strength of the relationship. It will change with units. If I converted all these numbers to cents, well, they would look very different, right? At least A and B would. Maybe R squared would stay the same. And there we go. That's sort of the quick overview of linear regression, how to do it on your calculator, how to predict values with it, some of the things to be aware of and be careful about. So what you're going to do now is you're going to do textbook problems page 204, numbers 37, 38, 41, and 42 as some practice here, just thinking about and working with some scatter plots and linear regression models. Then there's going to be a check-in quiz on the Nearpod. Please do that. Next week we'll dig a little more into regression models and working with them. The optional homework's on the weekly grid. Please do try it. I will post answers, I promise. This week has just been a little busy with the different tests going on. Office hours will be Monday. I will post people who need to be there today, so be on the lookout for your name. If you need to be there on Monday, please come. We're going to work through some things from this week that people maybe are struggling with, and then reach out to me if you need calculators. All right, everyone. I'll talk to you later. If you need help with calculators, actually, and how to use them, just reach out to me. I'm happy to help. Bye.